warm welcome here at DLD University, and the wonderful faculty and the dean and the counselor. I mean, I've never seen such a warm welcome like here, and also Dr. Venkatesh, who guided us through the wilderness of India, was very impressive. So thank you so much. Now we just heard an incredibly inspiring talk by Gustavo, my friend, and you heard his activity and the importance of, one second, I think something is here wrong. Computer. Not enough oxygen. Too much oxygen. There we go. So, why oxygen? And the reason we use oxygen actually was an invention by animals, because it's the most energetic molecule out in the periodic system. And so it allowed us to maintain something as complex as the brain, because it provides so much energy. But at the same time, it's like nuclear power. It's very dangerous. So too much oxygen is way more dangerous actually as too little oxygen. So if you have no oxygen in a tank, nothing much can happen. But if you have too much oxygen, it can blow up. So basically, our brain has to balance all the time to maintain oxygen enough to maintain our brain activity. And this brain activity is incredibly impressive. So when you listen to this activity here, this is what's going on in the brain. And you see that billions of nerve cells that have to generate constantly activity, and we generate this throughout our life. All these neurons are active. And whether you sleep, whether you're awake, whether you're excited, or whether you're inspired, your brain is all the time generating this activity. And this persistent activity requires a lot of oxygen, and it requires also a very close cooperation between the heart and the lungs. And that's exactly what Gustavo told us in his lecture. Basically, you need the heart, but you need also the oxygen from the lungs in order to maintain metabolic energy. But interestingly, the breathing is not only important to maintain the metabolic energy, but the breathing is also an important timing mechanism in our brain. So a lot of brain processes require input from our breathing centers. For example, this is activity from the prefrontal cortex, which is important for higher brain functions. And you can see that this activity in the prefrontal cortex is synced with inspiration. So when you all were inspired by Gustavo's talk a minute ago, then your prefrontal cortex was activated each time you have inspiration. And that's why all the gurus and the yoga people in India use breathing to concentrate and to focus the activity because of this neural signal of the breathing system. And this neural signal also is translated partially by other areas of the brain, like this is the locus ceruleus, which provides a lot of norepinephrine and activation of the entire cortex. So arousal is driven by inspiration. So each time, 95% of the time when you wake up at night, you wake up with a big breath, a sigh, because of this link between the breathing centers and these noradrenergic neurons up to the cortex. So there's a lot of metabolic energy needed from breathing, but there's also neural signals needed from breathing. And these neural signals come from a very, very small area, which we call the prebuccinal complex, which sits in the medulla. And this area syncs these signals throughout the brain and also balances your oxygen in your brain. And this area not only causes you to inspire, but it also coordinates your heart, because there's an area called the nucleus ambiguus, which contains your cardiovagal neurons that control the heart rate. When Gustavo talked about the pump and the lungs, then this is all controlled by this very area in your brain. And this very area in the brain is also seen functionally during each breath you take. So each time you take an inspiration and you take an exhalation, during the inspiration, your heart rate goes up and then your heart rate goes down. So this is an arrhythmia in your brain, but it's a good one. It's the one you want because it shows you that you have a healthy coupling between the breathing and the heart, and we call this the respiratory sinus arrhythmia. And there are many variations to this coupling that show you're healthy, and in one example of this is the so-called diving response. And during the diving response, we've heard already, the breath hold, you have to also adjust your heart rate. And we saw in the traces of Gustavo a minute ago that during this breath hold, the heart rate went down. And there's one animal where we learned a lot about this, which is the seal. So these animals can dive like for 2 hours, go 1,000 meters deep into the ocean. And you can see as they start to dive, their heart rate goes it almost stops. And there are only a few heart rate changes, because basically during this diving, the whole body of this animal is reconfigured. And in this animal, the entire metabolic rate of the heart, of the liver, of the lung, of the kidney, and other parts of the organs are all going down metabolically. And because they don't use much oxygen anymore, you can actually constrict your entire blood vessels in order to provide enough oxygen to the brain, because the brain is the one organ where you cannot compromise your metabolic energy. So to maintain this activity, you have to provide oxygen even during diving. Because these animals have to catch fish 1,000 meters deep, so they have to still provide this oxygen to the brain. And in order to maintain this, they compromise oxygen to the rest of their body. In a way, we do the same thing. So when we hold our breath, we also save metabolic energy in most of our organs, but in the brain we maintain metabolic energy. Now, if you can imagine you're diving for 15 minutes or for longer, then at one point your oxygen goes down. And so these animals, even though they have all this adaptation, they have to cope with hypoxia to maintaining this brain activity. And there's one invention that nature has done, and this is the neuroglobin. Okay, so in the brain, we have a specialized globin molecule that also can suck out oxygen out of the hemoglobin. And because it's only one chain compared to the hemoglobin, it has actually a higher affinity to oxygen. So basically, while we're diving, we can suck out oxygen out of the hemoglobin into the brain through this neuroglobin. And this neuroglobin is reflected in red color. So when we looked at the brain of these seals, you can see it's deep red. In fact, it looks like a steak. So Venkatesh, who is vegetarian, would never eat this brain here because it's full of neuroglobin. And this is the brain of a human. And after an epileptic surgery, and you can see it's totally white. So these animals have adapted perfectly to this environment. And when we looked at their neuroglobin, we were totally surprised, because in the mouse, the neuroglobin, the human also, it sits in the neurons. In the seals, it was sitting in the glia cells. And then when we looked at cytochrome C, we noticed that in fact they totally reconfigured their oxygen metabolism, because now the glia cells were sucking out the oxygen and the neurons were functioning anaerobically, whereas in the human and the mouse it's exactly the opposite. So there was a very specialized neuroglia adaptation in these seals, and when we looked at these neurons, even after 1 hour in oxygen, they would still generate action potentials, and they would actually, even if you take out a piece of tissue out of this brain, it would still generate this persistent activity. So these animals can maintain this metabolically highly energetic activity even if there's no oxygen. So you can see that basically these seals adapted to this diving behavior in a very special way by changing neuroglia interactions, but also by adapting the entire body, because as I said, they can go metabolically low. Now, humans also have adaptive strategies, as we just heard, and from Professor Subieta, but of course not to that extent, because I mean we can live in 3,500, but we cannot dive 2,500 meters down for 2 hours. Anyway, but again, like in a seal, during a breath hold, we do the same thing. Our heart rate goes down, it doesn't stop, but it goes down, and we have a healthy cardiorespiratory coupling. Now, in many diseases, and that's what we are very interested in this, in our research institute, this coupling is disturbed. And this is one child which has Rett syndrome, and you can hear her breathing. It's very heavy. So this is what she's doing during the day when she's awake. And now she goes into a breath hold. So she can go for actually several minutes into this breath hold, and they turn blue, and it's a very dangerous situation. And during this breath hold, there's a lot of changes going on in the cardiorespiratory coupling. So this is the trace of the same child. You can see during each breathing, the heart rate goes up, as you would expect. And then she goes into this breath hold, and you can see she starts with this diving response, but then the heart becomes independent. The heart rate goes up, even though it should stay down. And even when the child starts breathing again, you can see the heart rate doesn't care. So now you have an uncoupling of the breathing in the heart, and that's metabolically very detrimental, and it will actually cause a lot of oxidative stress in these children, and also a lot of hypoxic stress. So when we look at these breath holds, this child has experienced two very dramatic effects. One is it doesn't have enough oxygen, but when she also starts breathing again, she will suffer from oxidative stress. And this happens only during one of those breath holds, but it happens all the time, because what you just saw was one of those breath holds, and then she breathes again, and that's what she does while she's awake. She goes all the time into these intermittent episodes of hypoxic breath holding. And this is a feature that we see in very different neurological disorders. We see this, for example, in obstructive sleep apnea. You can see also we get an obstruction, we stop breathing, we get another obstruction, stop breathing. So we have intermittent hypoxia, which is a similar feature that you see also in familial dysautonomia. Also, when you look at these people that have epilepsies, during each seizure, they go into an hypoxic state, and then they rebreathe again, and they go to this oxidative state. So this is something called intermittent hypoxia, and that's something very, very different to what Gustavo taught, where you have chronic sustained hypoxia, which allows you to adapt to hypoxia, whereas in intermittent hypoxia, you cannot adapt to the situation because it's intermittent. And so a lot of the problems we're seeing are really due to this intermittent nature, which is very different to sustained. And this intermittent nature causes changes in your respiratory coupling, as I just showed you. And also when you look at the heart rate, these children have an elevated heart rate, and the heart rate variability, this interaction between breathing and heart rate, is also much lower, so the heart rate variability is decreased. You see this also in familial dysautonomia. You can see that their heart rate variability is much lower than control, both during the day and night. This is a trace where each line is one child, and this is the heart rate. You can see in these familial dysautonomic children, the heart rate is much more red, it's much more elevated compared to control, very similar to this. So there's a common feature of dysautonomia that we see in a lot of those children, which is increased heart rate, they have increased breathing rate, it's heavy breathing, decreased heart rate variability, and all of them also show sudden death, and we don't understand why do they have sudden death. And all these disorders are characterized by intermittent hypoxia, where you have an alternation between hypoxia and oxidative stress. And this is the same thing in epilepsy, it's the same thing in mitochondrial diseases, and multiple systems atrophy, and other disorders of dysautonomia. So the big question is, what's happening in the brain for this, and where is this coming from? And so what are the mechanisms underlying this cardiorespiratory coupling? And these mechanisms are sitting, again, in this very center for breathing, the pre-Bötzinger complex. And what you can do is, you can lesion this pre-Bötzinger complex in animals, and what happens then is the breathing stops. So this area is essential for breathing. So you need this very small area in your brain in order to maintain breathing. And it's not only essential for breathing, but it's also, one second, it's running away, but it's also sufficient, because you can take out this piece of tissue, and it's a very small tissue, in a mouse, and it still generates the breathing rhythm. And the breathing rhythm that this little tissue, this brain center, generates is very similar to the whole animal. So you have basically now a possibility to study the mechanisms, how this network responds to hypoxia, how it is affected by intermittent hypoxia. And you can really unravel the mechanism of this breathing. And as we referred in the introduction, it's all about complexity. So there's a very complex network that depends on three interactive properties. One, these neurons excite each other through synaptic mechanisms, so they depend on recurrent synaptic excitation. They have some bursting properties, and these bursting properties are very similar to what your heart has. These are pacemaker properties. So like your heart, you can take it out of the organ, it's still beating. You can take out a single myocyte, a cardiomyocyte, it's still beating rhythmically. And the same is true for these neurons here. They also have these pacemaker properties. And when you record from them, this is shown here in this movie, these neurons are driven during each inspiration, but you can block now the synaptic interactions, this one, and this is done now, and you can see these neurons continue to burst. So they don't need a network. They're intrinsically like these heart pacemaker cells, and they provide an important drive to this network. Now, these neurons, however, are very much controlled by inhibition. So in this network, these inhibitory neurons actually inhibit these bursting properties, because basically you don't want to have a machine that bursts all the time. You want to control it, because I mean, if I'm talking to you, I don't want to do all the time like this. So what happens is these inhibitory neurons actually shut down these pacemaker properties, so they're not bursting. And only when you take away the inhibition, then these heart pacemaker cells become independent and drive this network. Now, we also know a lot about these excitatory neurons within this network, and we have molecular markers that identify these very important neurons that drive your breathing, and these are called the so-called TBX1 neurons. And these TBX1 neurons synchronize together to form a breath. So you have these excitatory glutamatergic neurons that form a neural network to generate your breathing each time during your whole life. And again, these neurons are the essential components of your breathing network. So what we can do is we can genetically modify them, so we can put lysolides on it, and then these neurons can become active, so you can trigger, each time you shine light on them, you trigger inspiration. And also, you can inhibit them, so you have other opsins like opsin that can shut down these neurons, and then breathing stops. So these neurons are the essential component for your breathing. Now, surprisingly, these neurons cannot function all the time. So they have something called a refractive period. So if you have a normal ongoing breathing rhythm and you shine light on these neurons, right after a breath, you can elicit no more breath. So they're shut down. They have a refractive period. It takes several seconds until the next breath comes in. And so basically, you have a refractive period that prevents that the breathing rhythm becomes too fast. And but this refractive period is long. You can see it takes several seconds before you can initiate the next breath, which is very bad because these animals are breathing at 2 hertz. So they're breathing at a much faster frequency. So how can these glutamatergic neurons generate the breathing if they have this refractive period? And in order to solve this problem, we found out that basically this refractive period, this inhibition after a breath, depends on how excited these neurons are. So the more excited they are, the longer it takes for this network to recover from a breath. And so paradoxically, so we've heard about paradoxic situations, so paradoxically, if you stimulate these glutamatergic neurons during inspiration, what you find is that in fact the breathing slows down because you increase the refractive period. So these glutamatergic neurons, even though they're excitatory, they actually slow down your breathing because they increase refractive period. And so in order to regulate this, the network has at the same time inhibitory neurons that are activated during each breath. So during each breath, you are actually stopping these neurons from synchronizing too much, and they actually help you to overcome this refractive period. So If you block all these inhibitory neurons, you can see these neurons become extremely excited, but they also become extremely inhibited, and they slow down breathing. Whereas if you activate these inhibitory neurons, you decrease the excitability and you speed up breathing. So what this shows to you is that paradoxically, these inhibitory neurons, they can speed up breathing. So when you stimulate these inhibitory neurons during inspiration, you can see the breathing gets much faster, both in the slice but also in the whole animal. So the counterintuitive conclusion was that you have in your network a balance of excitation and inhibition. And the excitation slows down your breathing, and the inhibition stimulates your breathing, something which we totally did not expect. Now, what this means, however, that during each of your breathing, each of your breath you take, you have to balance all these different properties. So you have these excitatory neurons that form the beginning of your breath, but these excitatory neurons are inhibited all the time by inhibition until they reach the threshold for the burst, which then causes your inspiration. So during each cycle, you basically have to balance this excitation and inhibition to generate a breath. And this is actually quite a battle, okay? So during each time you take a breath, you engage in a battle between excitation, inhibition, and bursting in order to balance your breathing. And this becomes very important because in hypoxia can affect your balance and therefore change your breathing. Now, the key of this whole thing is that you have to balance the excitation and your inhibition. Because if you have too much inhibition, your breathing stops. If you have too little inhibition, your breathing becomes very rigid and very slow. It's like, and you would not sustain it. So all your life you have to balance your inhibition and your excitation in your network to maintain your normal breathing. And this balance is now altered in hypoxia, specific in severe hypoxia. So what happens is if you expose this network to hypoxia, then your breathing frequency goes up, and then you generate these sighs, and then you go into depression, and then you go into gasping. So this is basically your response that you show in response to severe hypoxia. And the gasping is very important because during this gasping, you try to resuscitate yourself to get back. And but what's remarkable is that this response is intrinsic to this network. So there's no carotid body here. There's no other higher brain center here. But these cells, they create your hypoxic response. And we studied this response for many years. But what's interesting is that every cell has a different sensitivity to oxygen. So the inhibitory neurons, early on during inhibition, shut down. Other pacemaker neurons shut down. And so you start to dismantle your network as you go into hypoxia. And then when you're in severe hypoxia, your network is driven only by these pacemaker neurons, like your heart cells, that now drive your respiratory network during gasping. So what you're doing is you do the same thing that the seal does as you go down. You shut down all your organs that you don't need in order to maintain something that can survive the severe state. So you shut down all your other calcium-dependent mechanisms, and now you depend on a sodium mechanism that drives your network. And this is actually anaerobically, and this gasping can last for a long time. During this gasping, as you lose also your inhibition, everything is active in inspiration. So when you go into a cold shower or you jump into cold water, then you do only inspirations because basically your inhibition is all shut down and all your other neurons are there. They're gone. So basically what I showed you is that the respiratory network generates breathing based on a fine balance between excitation and inhibition. And this network is intrinsically sensitive to hypoxia. So as you go into hypoxia, you shut down a lot of neurons that you don't need until you can get into this gasping network that depends on pacemaker properties that maintain your life in this state. So this network that I just introduced you controls many important functions, and that's responsible for your cardiorespiratory coupling. Because what we know is that this network sits right beside these cardiovagal neurons, and these cardiovagal neurons are inhibited during each inspiration. So during expiration, these neurons are active and they inhibit your heart, and when you go into an inspiration, then these neurons get inhibited, so the heart gets disinhibited and the frequency goes up. and then after this, the heart gets inhibited again. So you have basically an interaction between these neurons that controls your heart all the time, right at this very area of this brainstem. Now, so how can we study this now? So I told you that we can isolate this breathing center, which is very, very small. So how can we know that this is actually very important? And what we can do is we can use genetic tricks, and we can basically modify these cardiovagal neurons and make them light sensitive. So these are the cardiovagal neurons now, and they contain an opsin, which is channel rhodopsin, and this allows us now to identify these neurons and show that they are inhibited during inspiration, but we can also activate them using laser light. And we can do this laser light injection not only in the isolated state, but also in a whole animal. So here is the heart rate of a whole animal, and that's the breathing. Each line is one inspiration, and then you can see if we shine light on these cardiovagal neurons at the prebursal complex, the whole heart rate goes down. So you basically can show that these cardiovagal neurons indeed control your heart rate in the intact situation. And this also allows us now to tell you that your sinus arrhythmia is based on this area, on this very interaction that I showed you, because during each inspiration, these cardiovagal neurons are inhibited, your heart rate goes up, and then it gets activated, your heart rate goes down. So your coupling exists in this area. So why is this important? Why do we do all this? We do this because now we can ask the question, what happens to these neurons in hypoxia? What happens to this coupling? Because now we have isolated the mechanism, now we can go deeper into the underlying mechanisms. And what we find is that if we expose this network to chronic intermittent hypoxia, you get an upregulation of HIF1 alpha. So this is the reason we have the Nobel Prize, because this HIF1 alpha is activated by hypoxia and does a lot of other things, for example, in cancer, etc. So this gets upregulated in this network. But at the same time, what we find is that not only HIF is upregulated, but you get also oxidative stress. And this was another of our paradoxical surprises, because as you go into hypoxia, you start to produce hydrogen peroxide in these very neurons that control the breathing and that control the heart. So basically, when you go into hypoxia, your network generates oxidative stress. And when you go back, you also get more hydrogen peroxide production. So basically, the hypoxic stress causes oxidative stress. And this becomes very remarkable. So when we look at markers for oxidative stress after chronic intermittent hypoxia, this prebursal complex and also these cardiovagal neurons, they have generated oxidative stress. And that's exactly what we see also in Rett syndrome, in these children that have intermittent hypoxia. When you look at their brain, they have also signs of oxidative stress very much higher than what you see in controls. So basically, the breath holding is creating oxidative stress, but also hypoxic stress because you have the HIF upregulation. So the important conclusion is disorders associated with intermittent hypoxia are associated with oxidative stress. So basically, we can use markers for oxidative stress to show how much intermittent hypoxia these patients experience. So what does oxidative stress do to these neurons? So we can now start to ask this question, we can record from these neurons, and when you now apply hydrogen peroxide to these neurons to mimic this oxidative stress, you see these neurons start to get inhibited. So they shut down, and as they shut down, now you don't see any more difference between the expiration and the inspiration because they're inhibited. So what it means is the heart rate goes up, but also your heart rate variability is blunted because there is no more activity in these neurons. So now you have exactly this phenomenon that we